Thank you very much for the nice introduction. So good afternoon, everyone. So I will talk about strain silicon nanowire tunnel FETs and the inverters that we achieved in our institutes. So here's the So the outline of my talk, I have only covered these 4 parts. First is a brief introduction, then I will show some experimental results on the scaled strain silicon nanowire FETs and also inverters. Then the next part is just for the future work, what we are going to do for some new structures and the new materials that are available for the FETs. And finally, summary of my talk. So as you know that the conventional MOSFET has a physical limitation. Its substrate swing has a minimum value of 60 millivolt per decade at room temperature. This is why we cannot reduce the VDD to a very small value. So if you look at the curves, so if, for example, for the ideal case, if we have this number, and if we reduce the VDD for 60 millivolts, then we have to increase the off current by 1 order of magnitude. So this is why we cannot reduce the power consumption, because the power consumption is a function of VDD. So the ideal case is we have to somehow realize this very steep slope devices, but the tunnel FET belongs one of this family. So you see here that we can really achieve very steep slope device, steep slope, and also the off current can be very small. So the simulations from Intel shows that there's the very great expectations for FETs. If you compare here the output characteristic of the FET and the CMOS at very low voltage, this is below 0.35 volts. You see here the FET shows much higher on current and also very low saturation in this regime. And also their simulation further indicates that if the switching energy and the standby power consumption keep the same, then the FET logic works much faster than the CMOS with a factor of 8. So this shows very great potential for the FET for low power applications. So as you know, that FET is based on the band-to-band tunneling, and it's a gated PIN diode. It's here show the structure. You see here the source and the drain is oppositely doped, and here the band structure that in the on state. If we apply gate voltage, then the band bending. So then the band-to-band tunneling occurs at the source to tunnel junctions. But there's a lot of challenges for the FET. First is the on current. It's really very small, and then also we have to get a very steep slope for large range of the drain current, not only something like a minimum point slope. And also the third challenge is the bipolar switch behavior, because you can switch on the tunneling at the source or at the drain by changing the polarity of the gate voltage. So this bipolar behavior will increase the off current and also further increase the power consumption. Well, technically, there's 2 challenges. First is we have to achieve very steep tunneling junctions in order to improve the on current, also reduce the substrate swing. And the second, this is also the most important challenge, is for the trapezoidal tunneling. So if you look at this picture, you see here, if there's no trapezoidal tunneling, this is TAT, there's only band-to-band tunneling, always you can get very steep slope. But if the trapezoidal tunneling occurs, and also the trapezoidal tunneling occurs at very small gate voltage, it's much earlier than the BTBT. So in this case, you cannot get very steep slope, and also the slope is limited by 60 millivolt per decade in this case. So for the theoretical, so I would like to start with this WKB approximation. You see here this band structure. Then we can easily get this simple equation. So I mark 3 important parameters in this equation. You see here the lambda is grain length and the effective mass of the band gap of the semiconductor. So this simple equation just tells us what kind of materials and what kind of structures we have to use in order to improve the tunneling currents. So for the materials, we have used very low band gap materials with smaller effective mass. So for the group 4 semiconductor, silicon has a very large band gap. It's also indirect, so this is not suitable for the FET. But if we apply some strain on it, then we can reduce band gap. And also, if we move on to the germanium or germanium tin, also it's possible to realize direct band gap and with a very small band gap. So this also can be used for the FET. So the second part is for this screening lens. This is reflects the steepness of this band bending at the ternary junctions. You see here there are two parts. First part is from the junction doping. So this means we have to use very steep junctions. And also the second part is from the electrostatics by the gate control. So we have to move from planar to nanowire structures with a gate around. So now I move to my process that we developed in my group. So this is a very simple process. So first we pattern this nanowires arrays, and now this is a nanowires is a tensile uniaxial strain. So then we form the gate stacks with carbon oxide and titanium nitride, and then we do the silicization at the source of the drain. So instead of using nickel monosilicide, we use a nickel disilicide in our process. So this shows us the TM picture that what we grew single crystalline nickel disilicide on bulk silicon. You see so only 10 nanometer in the thickness, and if this is on a nanowire structure, if we cut along the nanowires using FET, so we get this cross section. You see here, or nickel disilicide. Also, we developed a process to use aluminum and nickel alloy, so we can realize this nickel disilicide phase. So you see here we have perfect alignment with the silicide to the gate. And also this silicide nanowire is also very uniform as thermally very stable. So the next step we do the boron implantation. There's a source drain implantation, I would say, because normally you see the TFET has a oppositely doping type as the source and drain. Normally you need masks to do the implantation, but now in our process we don't need any masks. We do the tilted ion implantation, use the gate as a shadow mask. So here, for example, here we do the boron implantation at 135 degree. Then we do the arsenic is 45 degree. And then the final step is do out diffusion by annealing at low temperature, which, for example, is 450 degrees C. So after that, due to the shadowing effects of the gate and also the Doppler segregation at the silicide gate, so we form these pockets at the edge of the source and drain. So here we have P plus, here is N plus. So we form this TFET structure. And also from the Simpson measurement for this kind of ion implantation into silicide, and after out diffusion, we see that the junction is really very steep. For example, here this is for the arsenic implantation of 750 degrees C, 1 minute annealing. So we get very steep junctions with 1.4 nanometer per decade. So but for the boron it's a little bit larger, but still 3.2 nanometer per decade. So this is just shows. Whereas we use this process, we can really achieve very steep junctions for the tunnel FETs. And then also here shows the band diagram of TFETs with these pockets, these doping pockets, and the N plus and P plus here. So if we apply gate voltage here, you see here the band tunnel occurs here. Now, there's some advantages that I list here. Use this process, use a single crystalline nickel disilicide, so we can get very steep junctions that I showed you before. That also we have perfect gate alignment and also lower source drain resistance because the metallic source drain. And the most important challenge is here, the advantage is this one, because we do the ion implantation into the silicide, not directly into the silicon. So this means we can create less defects in the silicon in the junction. This means we can also maybe suppress the traps internally. So here shows the structure that are done nanowire TFETs. You see here we have a thickness of 7 nanometers, and here the base is around 45 nanometers. Here we have 3 nanometer carbon oxide and titanium nitride as a gate. Here the output characteristics of the PFET and NFET. You see here for the PFET we still have a slightly S-shaped at the beginning here, but for NFET we don't see anything. It's a really linearly increase with the drain voltage. And also here to these 2 points, we focus on the VDS 0.5 volt, we can achieve the on current 10 micrograms per micrometer for the PFET and 18 micrograms per micrometer for the NFET. This is really large numbers if you compare to the published literature for the silicon and silicon germanium TFETs. So now this shows the transfer characteristics. So you see here the PFET, we still have minimum slope of 90 milliwatt per decade, because in this case the tunneling junctions is made by arsenic implantation. As you know, arsenic is very heavy. We did not optimize the implanted angle. It's just 45 degrees. So in this case, maybe there's some defects created in in the junction, still in the silicon part, and also that we do the annealing at very low temperature. Arsenic is so heavy, it's not so easy to activate. So this maybe the doping level is not so high. So we still have a trap system tunneling. But for the boron case, for the FET with the boron tunneling implanted tunneling junction, then you see here the slope is much better. If we draw a slope as a function of the drain current, then we can get a minimum slope of 30 millivolts per decade, and also below 60 is more than 100 magnitude of drain current. Of course, because we do the same doping at the source and drain, so the transistor shows very strong bipolar behavior. You see here that the minimum current changes with the drain voltage. But if we use a pulse measurement on the PFET, you see here this with the pulse measurement. So in this case, we can suppress the trap tunneling because the traps are not so fast as the pulse we used. So you see in this case, we can do here before we have a 90 millivolts per decade. This is the minimum point, minimum slope. Now after the pulse measurement, we can get much smaller slopes with less than 60 millivolts per decade at room temperature. So this shows that the trap assisted tunneling is really a problem for the TFET. This is a big issue for TFET. So we have to find a way to suppress it. So, and more results will be presented in the IDM this year. So also use this technique, we can easily to fabricate the inverter structures. You see here, we have two gate fingers, and we do the tilted implantation boron and also arsenic. In this case, we form the FET in this side, and also the PFET. This is tried with the common drain as the output context. So here shows the VTC characteristics. You see here that we have plotted VDD from 1.2 watt down to 0.2 watt. It shows very sharp transition. If you see here the gain from this extracted from these curves, you see here for the maximum gain we obtained at VDD 1.2 watt is above 55. Even for the 0.2 watt, the gain is still above 3. So this is really it's a good transition for these TFET inverters. And for the time response analysis, we show you see here this is the input signal, and with the black lines and the red line is the output signal. You see we do observe this overshot here and here. This is because the enhanced Miller capacity in the TFET. So also this you can see this theoretically paper from this this one. And the fall time in this case we measured is only 2 nanoseconds. Of course, it's not comparable to CMOS because the current level in this case is very slow. It's very low. So we try to further improve the TFET performance by using nanostructures with gate around. Now we move to 10 nanometer nanowires. You see here the titanium nitride gate with a gate around. Then the nanowires only has a diameter of 10 nanometers. So I did not show TM because I have we just made one TM. Its diameter something is less than 10 nanometers, something around 8 nanometers. So here's already silicited. If you compare these two nanowire transistors, one is with 10 nanometer, one is with 20 nanometer, you see this smaller nanowire transistor shows high ion current and smaller subresistor. You see here the comparison of the subresistor with the red one for the 10 nanometer, and here the black one is for the 20 nanometers. You see here the 10 nanometers device is this subresistor is very close to 60 millivolts per decade. And also in this process, we do the lower doping level at the drain side, so we can suppress the bipolar behavior you see here. And also, if you look the output characteristics of the 10 nanometer nanowire transistor, you see here the current is really high. If we move to the VDD is 1 watt, then we can get some around 75 microamps per micrometer. So in this case. And also we do some temperature dependence measurement for different structures. For the planar TFETs, is a tri-gate nanowires with this width of the nanowires 18 nanometer. The thickness is already almost the 7 nanometers. So also here's a 14 nanometer with a tri-gate, and now it's a gate around with 10 nanometer nanowires. You see because the trapped tunneling is always occurs at higher temperature, if you lower the temperature, always then the traps are frozen, so there's no TAT occurs, and you see this why at the lower temperature that the substrate swing is constant. But if you compare the room temperature for different structures, for say that the substrate swing decreases with the decreasing diameter of the nanowires. So this means if you increase the electrostatics, the trapped tunneling is really suppressed. So this means the impact of the trapped tunneling in a very small nanowires is really much less. Here just shows benchmarking of our device with some published papers. So here these blue points is from our work, and also the green ones is mostly from silicon and one is from germanium transistors. And you see here I have the three-dimensional. Here's on current. Here's a minimum substrate swing. Here's off current. Of course, it's the on current our work is in a quite good position, and the minimum substrate swing and also the off current is also is quite okay. So I will point out this value. This one is this red point is from the Intel paper that's published 2 years ago in IDM. They used the VDD is 0.3 volt. But if we compare all points, this one and this one for 0.3 volt, I see there shows it's almost comparable performance. So if you see that for the low power application, so if we target the VDD is 0.3, so the targeting current should be around 2 microamps per micrometer. But if you compare our transistors, we are still 1 order of magnitude lower than this targeting value. So this is why we are trying to increase the strain to reduce the band gap, increase the tunneling probabilities, and also we can also introduce some new materials, group 4 materials like strained germanium tin, because these materials can be direct band gap. So for the strain, so we use the concept that's developed by PSI group in Switzerland. What they did, they started with the biaxial tensile strain silicon on insulator. Then they patented nanowires with 2 large pads. After that, they etching the oxide below, and in this case, the strain in the pads will be relaxed, and the strain in the nanowire will be increased. So they measure the strain. They got a maximum strain of 4.5%, and also in this case, the band gap of silicon is reduced to 0.5 EV. So we try to use this concept to TFET, and we also try to use locally increase the strain at the source to channel junctions. In this case, keep the drain side as a lower strain level in order to suppress the bipolar behavior. So this you can see the poster by Lars. So for the new materials, we also try to integrate the silicon germanium tin also with, for example, here the heterostructure TFET with germanium tin as a source, strained germanium with its tensile strained germanium as a channel, and the silicon germanium tin as a drain. Here shows the TM picture for the growth of the strained germanium on a relaxed germanium tin with a tin content of 10%. You see here from the XRD environment, we show that the germanium has a strain of 1.2%. So in this case, we can have this direct tunneling at the source from the gun point to gun point. Okay, so this is just same profile that shows that all the layers has the concentration of the germanium concentration is quite uniform in the layers, and also the interface is very sharp. And also we do also the growth is of this heterostructure silicon germanium tin with a boron doped. It is in situ dope, and here also shows the same again that the boron is doping only in the silicon germanium tin, and that's the high resolution TM shows that the top germanium layer and also here silicon germanium layer is very, very nice with single crystalline quality, and also the interface is also very nice. And here show the lower interface, the germanium tin to silicon germanium tin. So it's also quite nice. Okay, now let me to conclude my talk. So I showed you that we use the implantation into silicide and also a low temperature driving out annealing, and with dopant segregation we can really get very steep junctions. And also I showed you that using nanowire structure, So it's better to use the very small nanowires with getting around. We can obtain this high ion current with 75 microns per micrometer at 1 watt. And also I showed you that if we scale the nanowire diameter, we can suppress the trappist tunneling and also decrease the subresonance. And also I show you that with using our first T-FET inverters, and also it shows high VTC gain and also shows very sharp transition even at VDD of 0.2 watt. So for the future work, we are working on the highly strained silicon nanowire structures, as I showed you, and also we are try to use strained germanium, silicon germanium, these direct materials with a smaller band gap. So this material could be competitive with 3.5 materials. So finally, I would like to thank my colleagues for the contribution, especially for the PhD students, and also thank for our project partners for the very nice collaboration. Thank you very much for your attention.
Okay, the paper is open for questions.
So there are two mechanisms for switching. I should mention that this is very interesting work because the prospect is to lower the voltage in electronics. And we heard this morning from Michael Taylor that if we could do this, this would be his fourth horseman, which is an act of God. Okay, so this is very hard to do. But we need to try to understand the mechanism. Now, there are two mechanisms. So one mechanism is to modulate the distance of tunneling.
Yes.
And the second mechanism has come to be called the energy filtering. At the band edge, you have a sharp cutoff of the energy levels. And so that's a second mechanism for sudden switching. In your work, which mechanism do you think it
I think
is?
the first one, because now we try to get very steep junctions, and also this means the band is very sharp, then the tunneling distance is much smaller.
So you think you're modulating the tunneling distance, but the
Yes.
problem with that is that it's a well understood mechanism, and it doesn't lead to. It leads to some steepness, but not at the higher currents that you're more interested in. So shouldn't you be going over to the energy filtering mechanism?
Yes, maybe it's because now we are planning to the next project. So maybe you know that in Europe we have the E2 switch, and we have different concepts. This also is also included in this one. Yes.
I have a question. You said that the trap-assisted tunneling is much less in nanowires, but could you explain why?
This is not much less, because I think that the impact is less, because if you have the nanowires, because the electrostatics is much better, this means this band is much sharper. In this case, the tunneling efficiency is much higher. So this is just the trappist tunneling is just other advantage. The impact is less. Yes.